you get your pracs back, that the marks have gone up quite a lot from what they initially were. And that's because things like, so basically in previous years, more marks had been given for doing things like actually identifying the rock on the trip around campus, or so, you know, actually for you being able to work out what it was that you were looking at. And I think when you have geology grad students, this stuff is something that they do every year from first year right the way through, and so they think that that part of it's really easy, and so they give more emphasis on things like the observations made. And it's harder to get all of the possible observations, so then the marks end up being lower. So you'll see that the marks have been gone up a lot. You're not being treated any differently from previous years. So they've been moved up so that they're in line with what has been happening previously, if you see what I mean. So if you see marks have been changed, that's why it has happened. The other thing that I would say is that, and this is something which commonly happens if you ask, so the demonstrators are learning how to mark things as well, and this is why they get moderated. This is why you need to moderate them. And Trish has told me there were a couple of places where they might have made slightly, I guess you could think of as snarky comments, which, if that has happened on any of your questions, I apologize for. It isn't acceptable, actually. I mean, I think they think some of these things are easy, and so they're like, think that it's obvious and then say something slightly snarky. They will be told, there'll be a kind of, we're having a discussion to give them feedback on it as well, and we'll tell them that that isn't professional and is the wrong thing to do. And it's basically coming from the fact that they've had a very different training to you have. So some of the things that get drummed into them for a long time, they think are obvious, when in actual fact they are not obvious if you're coming to it from an engineering background. So I just wanted to say, if there is anything like that, yeah, it's only one or two things, but I just wanted to let you know. So in this lecture, we're going to talk about plate tectonics and continental drift. And this is leading up to the lecture next week, where we're going to talk about earthquakes in terms of a geological hazard. And I just wanted to say, for this lecture, a good resource, a good place you can find some more information. And I don't necessarily expect you to go out and buy textbooks. Like, I know that this is not your principal course this year, but this book is pitched at quite a popular level. It's quite a well-written, nicely illustrated book. It's less expensive than a lot of academic textbooks. So if you have found material in the course interesting, then that might be somewhere that you might want to go and have a look in the library. And it's good on the stuff that we're going to be talking about today. It's also good on quite a lot of the stuff that Robin Pickering is going to be covering later in the course, so after the end of next week. And one of the things which I would like you to realize about continental drift and plate tectonics is that it really is a very modern theory. It really is something which has only really been discovered and understood quite recently. So there's a quote here from the book. Have most of you heard of David Attenborough? Do you know who he is? So the guy that does the wildlife documentaries. So he actually trained as a geologist when he was at university. And there's a quote in this textbook from him which basically says that the professor of geology in the University of Cambridge read our petition with care. So this is David Attenborough. We were a group of geology students in 1946, and we demanded, in the way that students are prone to do, that our lectures should examine the theory of continental drift. Our professor explained firmly, when someone could demonstrate to him the existence of the unimaginable forces in the earth that would be needed to make continents move around the surface of the globe, he would lecture about it. But until then, the proposition was moonshine. So we went back to our lectures in this and other departments and tried to make sense of the convoluted explanations that we were given about how, for example, dinosaurs managed to get across the oceans from North America to Australia, and why Australia's spectacular Banksia plants should be so extraordinarily similar to the beautiful proteas of South Africa. And we were not allowed to dream about Gondwana. So it was only really in the 70s, around 76, where that condition was met, when they actually found out what the unimaginable forces were that allows the continents to move across the globe. So, to understand how it can happen, you have to understand the structure of the Earth. And you've probably already seen something like this before, but the idea is that we have this very thin layer, thin being 30 kilometers or so, of crust, which is what the rocks that you commonly see around you are made of, or it is made of the rocks that you commonly see around you. Below that, you have the mantle, which is still a solid rock. It's a peridotite. It's a particular type of rock. And then it is solid, but it's relatively hot, and so it can flow. And then deeper within that, there's the core. The core is mainly made of iron, and the outer core is a liquid, and the inner core, because it is under such high pressures, is made of solid iron. So it would look something like this. This is an example from a meteorite, an iron-rich meteorite, and these reach Earth because another older planet has been destroyed in a collision with an even larger meteorite, and so bits of that core end up being thrown through space and eventually fall to Earth as meteorites. So this is how we can see what our core looks like and is probably made of actually in our hands. And so you have, yep.
Temperature becomes hot.
As you go down, the temperature increases. What causes the increase in temperature? So there are a couple of things. So first of all, you just have the initial formation of the Earth, okay? So the collisions where lots of different material came together to actually form the planet itself. And when you have those collisions, they produce large amounts of energy, right? So you get heating because material is crashing together. And it takes a very long time when you have something as large as the Earth for that heat to flow outwards and to be lost to space. But if it were just that, the Earth now would be solid to the core. It would be cold and most likely dead. And the reason, and there were people, there was a guy called Kelvin who actually calculated the age of the Earth based on this. He said the Earth must be younger than this number of years because otherwise it would have cooled down, all the heat would have escaped. The thing that he didn't know about, and the reason why it is still hot, is because you have radioactive elements. So actually radioactive decay of radioactive elements, which are often large amounts of them in the core, that heat production is what means you still have a warm Earth today. So basically you can think of the Earth as gradually cooling. The inner core is actually growing. So as it cools slowly, the core solidifies. So you get outer core material freezing onto the inner core. So gradually we are losing heat. Gradually it is getting colder and colder. The reason why it hasn't lost all its heat completely is because of radioactive decay. Okay.
Isn't it hotter at the inner core than at the outer core?
So the inner core will be hotter than the outer core, and the reason that it's a solid is because at higher pressures you can be a solid even at higher temperatures.
The inner core growing because it seems as if the liquid outer core.
Sure, but for a given pressure, the lower the temperature, the more likely it is to be solid. Okay, so basically because the whole thing is cooling down, that boundary between solid and liquid is gradually moving outwards and it's getting larger and larger. And actually this loss of heat that we've just been talking about is what drives continental drift. It's what drives plate tectonics. So if you look at the temperature within the Earth, so the geotherm we just call the temperature within the Earth, you see that it will look something like this. So you have this very narrow band, which we call the lithosphere, where the temperature changes very quickly from roughly 0 at the surface to something which is much higher, so around 3,000, well, not quite 3,000 on this. Yeah, so if you projected this to the surface, it would be 1,300 degrees C. That would be the temperature if you projected this gradient to the surface. And that narrow area at the top, which is where the temperature changes very quickly, that's where the Earth is cooling through conduction. So conduction, if you think about heating up one end of a metal bar, you end up transferring that heat through the process of conduction. Below that, where the temperature changes relatively slowly, that layer is able to flow. And so it rather transports heat through convection. Okay, so you're heating up the material at the base, it then becomes less dense and is able to rise, and then at the top you end up cooling the material that's against the lithosphere, that's against the conductive layer, and then it can sink down. So it's the same way as you're heating water in a kettle.
Convection in solid.
So this is something which is a common misconception, which is that solids can't flow, okay? So if you have something which is a liquid, then it's kind of obvious how it can convect. But actually, over very long time scales, things which are solid rock, can actually flow. So I guess one way of thinking about it would be something like wax. Like if you heat up wax slightly, it can flow, but it's still a solid, okay? And so if you think about the rock, if you think about the mantle, that can actually flow in a similar way to wax, over long time scales.
So we can't really define anything as solid, because any solid can be a liquid that's very high viscosity.
So there's a difference between a liquid and a solid, which is different from the idea of something that can flow and something which breaks, okay? So you can have material which is a solid, but which is ductile, so it can flow. The definition is more about how the atoms within the material relate to each other, how they interact with each other, so basically the atomic framework. Does that make sense? And if you take a particular material at a low temperature, often when it is a long way from its melting temperature, then it will deform in a brittle way, so it'll break, so it won't flow. So we call that brittle deformation, okay? But as you heat it up, it's still a solid, it begins to be able to flow, and then it is able. So sometimes you would refer to it as a fluid, so it behaves in a fluid-like way, but it's still not technically a liquid, if that makes sense. The common example, which, actually I'm not, so the common example that's usually given here is if you have glass. So apparently if you go to very old buildings, you'll often find that the glass at the bottom of the window is thicker, and that might be because it's, so I've also heard it said that that's actually a myth, and it's something to do with the way in which they used to make glass, and that if you go to some buildings you can find it the other way around, so that it's thicker at the top. So. But yeah, that's something that you might well come across elsewhere. And it's this, and it is the flow of, and actually the flow, the convection within the asthenosphere is quite energetic. And it's this flow that exerts a shear stress on the base of the lithosphere, which causes the movement of the continents. So it's basically driven by density differences due to differences in temperature. Okay, so first of all, I'd like to talk a bit about continental drift. So this was proposed by Wegener just after the turn of the last century. And he basically noticed that many of the continents seem to fit together if you compare the two sides of the oceans. And he was one of the first people to propose that this was because they were actually connected and that they moved apart. And it was largely ignored and criticized as being unrealistic. But over the next few decades, you would see increasing lines of evidence. So the first person to actually notice the fit between the continents was an Italian back in 1858, and it was Africa and South America, and North America as well. He saw the shape of South America and saw that it naturally matches with that right angle in West Africa. And that's one line of evidence. When people look closer, And a lot of this work was also done in South Africa as well. Actually, they noticed that the assemblages of rock, so the ages and types of rock, also seem to match each other across this continental boundary. So one example of it, another example would be that in South Africa, but also in Antarctica, you find beds of coal, okay? And coal is made when you have large amounts of plant matter, which then die and are deposited in an anaerobic environment. And the types of places that you see those processes happening on the Earth now are generally at relatively low latitude, so near to the equator. But obviously, Antarctica is currently right on the South Pole. And so that's, again, something which suggests both that these areas were connected because they had the same type of environment, but it also suggests that that environment was closer to the equator than where they are now. And as well as the types of rocks, also the fossils. So this is one of the things that David Attenborough was speaking about. So this is a Mesosaurus, and it's found in South Africa and also in South America. And this creature, you can think of it as being somewhat, I guess, well, it's a predator, and it lived in shallow waters. Okay, so this was something that would be living in shallow waters. It would not have been able to swim from Africa to South America across the open sea. Think of it as something like a kind of crocodile type mode of living, okay? So not something that would have been able to cross the South Atlantic, and yet its distribution, as you can see, is throughout South America and Southern Africa. And there are other examples as fossils as well. So there's plant fossils are where a lot of these suggestions came from. So Glossopteris, which is another type of plant fossil. So one of the things which contribute to these coal deposits that we were talking about before, and those are found in a range across Southern America, Africa, and also Australia, India, and Antarctica. So all of those southern continents, you see the same types of plant fossils. They also seem to be things which you would expect to be growing in a warmer climate, so at a lower latitude, so further from the pole that you currently see. So we've got the shape of the continents. We have the fossil record, and one of the key pieces to actually get this theory accepted as fact came from what we call paleomagnetism. Okay, so paleomagnetism is a way in which the rocks record the magnetic field of the Earth at the time that they formed. So you can think of some minerals as being like little needles, little compass needles. So one example is the appropriately named magnetite, which has a large amount of iron in it. And there are various ways that this magnetite can become aligned with the magnetic field of the Earth. So if you have a volcanic rock, if you have something like a basalt, at relatively high temperatures, it's relatively easy, even though it's a solid, for the same reason as we were talking about before, for the minerals inside it to move, to rotate slightly. And at high temperatures, the needles of magnetite will align themselves with the magnetic field of the Earth. And the Earth has a magnetic field, that's why compasses point towards north, and that's also being generated by the convection, this time of the outer core, so the liquid metal core of the Earth. And if you look, and as your basalt cools, it'll cool below a certain temperature. Above the temperature, the magnetite will point towards the North Pole. It will rotate until it's pointing in that direction. Below that temperature, which is called the Curie point, that direction is frozen in, and it can no longer move. It can no longer rotate. You can also get it in sedimentary rocks. You can think of the the minerals, the little grains of the mineral as being like little compass needles gradually settling. And as they fall through the water column, they'll preferentially point towards the North Pole. And then when they get more sediment deposited on top of them and it lithifies, those are then frozen into position. And the reason I'm telling you about this, the reason I'm telling you about paleomagnetism, is if you look at a rock in a particular area of a particular age, paleomagnetism, sure. If you look at a rock of a particular age, you can measure by basically looking for the very small magnetic field that's produced by the minerals. You can measure the orientation of those grains. And if you do that in different areas, so if you do that for rocks in North America, you can map out the direction which those grains are pointing towards the pole, the magnetic pole when they formed. And if you do that, the pole seems to move. Okay, so there is polar wander path is how it's sometimes described. And if you do that for rocks in different continents, if you do it in North America, each of these points is a different geological time period. And you do it for Europe, so you have the same thing. You have each point representing a different geological time period. They end up both, if you look at very modern rocks, they would both be pointing towards the current North Pole. But you can see that these two paths, these polar wander paths, are not the same. They don't lie on top of each other. Now, if you think about what that means, if you had a continent and the pole itself, if the magnetic field of the Earth was changing, that means the apparent location of the pole would change through time. If, on the other hand, the pole remains fixed, but the continent is moving, that would also seem to give you an apparent change in pole. And the fact that these two lines don't lie on top of each other, if it were the pole that were moving and the continents were staying fixed relative to each other, then yes, you might see a polar wander path, but rocks of the same time in the different continents should both point towards the same place. Okay? So the fact that these two polar wander paths are different means that it's not the pole that's moving. The pole does actually move a little bit, as we'll talk about, but this wander path is not being controlled by that. It's being controlled by the fact that the continents are moving relative to each other. We'll talk about that in a few minutes. And so you can actually use this to reconstruct how the continents have moved over time. And so over time, you'll see that there have been a series of very large, sometimes called supercontinents. So these are periods when all of the current continents were close together. The one that you might well have heard about is Gondwana. So that was when Africa was connected to India, Antarctica, Australia, and Southern America. And since then, gradually, you've had this splitting up of the continents until you end up with them in the configuration today. So for this part of the course, I don't expect you to be able to reconstruct what Pangaea or Gondwana looked like. This slide is just to make the point that you can use the magnetic poles to get some idea of how the continents have moved relative to each other. And, okay, so that is the strongest evidence for continental drift. Okay, and continental drift is basically just that the continents are moving relative to each other. So that's what the theory of continental drift is. You've probably also heard of plate tectonics, okay? So plate tectonics is a related but slightly more complicated theory, or we add something to it. So if we're talking about plate tectonics, what we mean is the continents are moving as rigid plates. So another way of saying that is the interiors of the continents are rigid. They're not deforming. They're not changing in shape. And all of the movement, all of the deformation is happening in narrow bands between these plates, so at plate boundaries. And if you look here, so this is looking at South America and Africa, and you have the Atlantic Ocean here. The red circles are earthquakes, and you can see indeed that there are certain places, such as through the center of the Atlantic, where there seems to be a line of earthquakes. So the earthquakes are showing you where the deformation is happening, and so that's one piece of evidence for plate tectonics. So what I said was what continental drift is. All that continental drift means is that the continents are moving relative to each other. So they're getting further away from each other, or they're coming together. Okay, so they're not, the configuration that we currently see on the Earth today is not always the configuration that there has been in the past, that they've come together and moved apart. Okay.
Tectonics, are they also not moving?
So they are still moving, which is why it's a connected concept. But the thing that we add with plate tectonics is we're saying that that movement is only happening at the boundaries. Okay, so the interiors of the plates are rigid, and the boundaries are where all the movement happens. And if we do that, we're basically talking about the movement of rigid plates on the surface of a sphere. And if you have a rigid shape plate and the movement is only taken up at its boundaries, then it will obey this equation, which is sometimes called Euler's theorem. And it's basically the equation that you have that relates linear velocity to angular velocity. Okay, so omega is the rate of rotation. R is the distance from the pole around which it's rotating, and v is its linear velocity. So the way of thinking about this, if you think about a record, like a record or a CD, it's rotating about its central point. So it's going to be rotating at a particular speed, so it might do one full revolution in, let's say, 1 second, okay? But if you think about how far a point close to the center is moving in 1 second, the linear distance is the circumference of that circle, so it's relatively small, whereas as you move further out, the linear distance is much greater, because again, it's the circumference of the larger circle. And so this equation is just a way of relating the linear velocity, so how fast it's moving in meters per second, to the angular velocity, or how many degrees per second it's rotating. And the link between them is how far away you are from the pole of rotation. And if you look at GPS vectors in many continental regions, so North America is quite a good example of this because we have quite a lot of pieces of data. Each of these arrows is showing the velocity of a point on the ground as it's moving, as shown by GPS. And you can see that these arrows seem to have a somewhat circular pattern, right? And you can see that they're rotating around a point somewhere around here, okay? And how did they map points of flotation? So this whole area, oh, you mean like how come there are arrows in the oceans, islands? That's what you have to do. So yeah, it is a problem. So you can't really get good GPS locations in oceanic areas. So we will talk about the oceans in a second, because this is also where a lot of the evidence for this plate tectonics comes from, and it was originally looked at in the Atlantic, and we're going to talk about magnetism again. So the mid-Atlantic ridge is this zone of shallow bathymetry, so the ocean gets shallower as you approach the center, and the dark points on it are earthquakes. We saw this area before, we saw the red circles, so there's a line of earthquakes, a line of deformation along the mid-Atlantic ridge. And what's actually happening here is as North America and Eurasia, or South America and Africa are moving apart, you create a rift in between. And as the two plates are pulled apart, the hot asthenosphere can reach closer to the surface, and this produces volcanism, this produces melting. And that melting creates new oceanic material, new oceanic crust along this ridge. And then it gets pulled apart, it gradually cools and moves in either direction away from the ridge. And this was actually, I would say, probably the single piece of evidence that really convinced everyone in the community that this was really happening, that plate tectonics was actually accurate. It was when people started taking measurements of the magnetism, so the orientation of those little needles of magnetite, which were formed within the oceanic crust. So the oceanic crust is entirely made out of basalt, and it's quite rich in these magnetic minerals. And so you can actually measure them from a ship just by doing swathes back and forth across the oceans. And what they found was that the map of magnetic intensity, magnetic direction that they observed in the mid-Atlantic was striped. And that stripe is because in some of these areas, the brown areas, the magnetite, the paleomagnetism was pointing towards the north, pointing towards the current North Pole, which is the current magnetic pole, whereas in some of them, which is shown in blue here, it was actually pointing in the opposite direction. Okay, so it was basically pointing much closer to the South Pole. So that magnet has flipped its dipole. And that is something which does happen. So every few 100,000 years, it seems that the Earth's magnetic field becomes unstable and then reestablishes itself pointing in the opposite direction. So it goes from north positive, south negative to south positive, north negative. Okay. It's actually quite interesting what might happen. We don't have a good idea of what happens during that changeover. So there may well be a period of time where you have chaotic flow within the outer core where you don't have a strong magnetic field. And that is potentially a problem because it's the Earth's magnetic field that deflects a lot of the solar radiation. Okay, so there could be problems with that when it happens. It's every few 100,000 years, so it's not regular, it's not clockwork. So I think I'm right in saying, and I could be wrong about this, that the average is something like of the order of 100,000 to 200,000 years. And I also know that it's been more than that since the last time it reversed. So you could say that we are overdue in some sense. It's been longer since the last reversal than the average time between the reversals now. Okay, and so the reason that I'm talking about this now, the reason that it has this, the reason that we would talk about this in terms of plate tectonics is that these stripes of positive and negative, are basically symmetrical. They're mirror images of each other. So you would have a positive north-pointing magnetic period, which is currently happening, and then on either side of that, you would have two equal thickness bands of negative pointing towards the south, and the same moving outwards. And what people realize, you notice that these are not all the same width, so here is a timeline. So you can actually work it out from this. So you asked how long on average. So this is 1 million years, so 100,000 years would be about a tenth of this. So this is about 100,000 years, this is about 200,000 years. So you can see it's the right order of magnitude. Okay. So you get this repeated pattern, and people realize that the way that you got this repeated pattern was because actually this Gaussian, this period, formed at the same time as this period, but then it was separated in half by the rift, which was constantly spreading. So this was formed at the same type of this. They were originally together, but then as the spreading continues, they've been ripped in half and moved apart. So that's what's happening during the current epoch now. Does that make sense? That's maybe something which is, so basically what I'm saying is, let's say, a positive period, and it's forming by rifting along here. And then at some point, all of a sudden, you are going to start having a negative period. So I'm going to put the negative period in blue. And on either side of that, you're still going to have this positive material. And so this is then going to be a mirror image. The negative period will grow. And then you'll have another reversal, and so another positive period will start forming in the middle. Okay, does that make sense? So that's how you get this symmetrical pattern, because the two halves, which are mirror images of each other, are once together and they've been rifted apart. They're continually being rifted apart. And you can use that to map out the age of the ocean. So you can look at this pattern, you can count how many reversals there have been from the present day, and you can work out the age of the oceans. And so here, if we look at the Atlantic, you have the younger material at the bigger, closer to the ridge, and it gradually cools as you move. It gradually gets older as you move towards the continent. You can see that in some areas, for a particular age, the color here is giving you the age, the area is much wider, and that's because some of these ridges are opening much faster than others. Okay, so you have different spreading rates at different ridges. And you can actually predict what the spreading rate will be by how far away they are from these poles of rotations that you can get from GPS. Okay, so one last thing for this lecture. We've said that we expect our poles, we expect our GPS vectors to look like, to follow Euler's theorem. So basically to be radial, and as you move away from the pole of rotation, they should get larger and larger, okay? So one effect of that is that as you move perpendicular to the vectors themselves, they should get longer and longer, or shorter and shorter. So the magnitude should change as you move perpendicular to the vectors. If you actually, and that's what we're showing here. So if this is the pole, we move away from the pole, we're moving perpendicular to each of these vectors, and the vectors are getting longer and longer. If you look at some areas in the continents, particularly, this is India, this is Eurasia, you can see the opposite. So the vectors are pointing more or less towards the north, but as we move north, so parallel to those vectors, the magnitude is changing, okay? It's getting smaller and smaller. And that is a sign that in this area, we do not have plate tectonics, okay? We do not have this rigid shell rotating around a sphere. And if you look at the earthquakes in this area, and we'll talk a bit more about this in the practical on Monday and next week, if you look at the earthquakes in the area here, you can see that there are some areas which look like what we saw in the Atlantic. So we see these narrow bands of earthquakes. But then there's also a very large area north of India, so Tibet. These are the Tian Shan Mountains. This is basically places like Kazakhstan in the north, western China, where rather than having a narrow band of earthquakes, you have events spread out over a very large area. And you can think about what's happening here actually as India moving northwards. It does appear to be relatively plate-like. There aren't many earthquakes in the interior of India, but it's actually causing Eurasia to the north to crumple up over a very wide area. So not a narrow band, rather a wide region. And this obviously has implications for earthquake hazard and knowing where you're likely or unlikely to have an event. Do you have a question? Okay. And if you look globally, so these next two pictures are not in the handout because I didn't want to print this much black. But basically, what I'm going to show you now is a distribution of the earthquakes in the oceans and the distribution of earthquakes in the continents. So this is in the oceans, and you can see that you generally have these very narrow bands of earthquakes going through the centers of the oceans and then along these boundaries at the edges of the continents. And if I now look at the earthquakes in the continents, in some places you see something similar, but generally speaking, you see a much greater distribution. So particularly in this area here. This is sometimes known as the Alpine Himalayan belt, because it's basically a region of collision that goes all the way from the Alps in the west to the Himalayas in the east. So the ones which are at mid-ocean ridges, which are a long way from the continents, it's unlikely that there's going to be anybody there to experience them. But then if we went back to the, if we go back to the ocean picture, you also see there's a lot of earthquakes along some of the edges of the continent, so places like South America. So what's happening here is you have a plate boundary where you have oceanic material which has been subducted underneath continental material. Okay? And so those are often very large earthquakes, and they often do cause damage, they do cause shaking, but even more importantly than that, they also can form tsunamis as well. So if you have a fault below the sea, so let's say, as you would generally find in one of these earthquakes, this type of fault, so this is a reverse fault or a thrust fault because the hanging wall is moving up, what that will do is when it happens, which will be, the actual failure itself will happen in a matter of seconds, and it will actually move upwards and then displace the surface of the ocean above it, because water is incompressible. So if you push it up from below, the entire water column is going to be raised. And what happens then is, because this is a fluid, because it's water, this is then going to collapse in that direction due to gravity. And so this is one of the main reasons that you have tsunamis. Okay, so this is how a tsunami forms. You have one of these earthquakes which push the seafloor up, that then displaces the top, the whole water column, and then because you have a column of water which is then higher than the column of water next to it, that can then travel very long distances over the entire ocean and cause inundation. So for instance, in Japan, where there was the earthquake which caused the damage in the Fukushima, the nuclear plant, a few years ago. It's sometimes called the Tohoku earthquake. The actual shaking itself, even though it was a very strong earthquake, didn't cause a huge amount of damage. And that's basically because they're so good at earthquake engineering in Japan. They know that there's a risk there. They know they're on a plate boundary. They know they have regular earthquakes. And so they build buildings which can withstand them. But actually, the tsunami was larger than they were expecting, and so the tsunami defenses were not up to sufficient height to stop it moving inland. And that was what caused the vast, vast majority of the casualties. So, yeah, I think I'll talk a little bit more about why that was wrong in the next lecture, or why they did that wrong. Okay. And so we're going to talk about this a little bit in the practical, but I just want to give you this little piece of information because it will help you to understand the practical. But one thing which you can ask is, why do we get this difference in behavior in the continents? So if you remember, we said that the oceans in general seem to be very much plate-like, whereas in the continents you seem to get earthquakes being distributed over a wider area. And one way that you can think about this is that actually, effectively, the continents are relatively weak, or a bit squishier than the oceanic material. And we'll see a bit more about why this is in the practicals. But the key difference, the main difference, is actually that the continents are hotter, they're warmer. So remember we said that as you get hotter, as you get closer to the melting temperature, the material can deform much more easily. And the reason that the continents are hotter are both because the crust is thicker and the crust is relatively poor conductor, so it acts like a blanket. It keeps the geotherm hotter underneath the continental areas. So the crust in the continents is about 30 kilometers thick, whereas in the oceans it's around 7 kilometers thick. But also, and this is not, okay, and another piece of information which isn't on here, it's useful to know perhaps, because of the chemical composition of the continental crust, it has more of those radioactive elements. So you remember we said that the reason that the Earth is so hot was because of natural heat produced by radioactive elements. There are more of those radioactive elements in the continental crust than you find in the oceanic crust. And that's another reason that continental regions are generally hotter and therefore easier to deform, and so you get the deformation spread more broadly. Okay, and that is good timing, because I think we have some practicals to give back to you now as well before you go to your next thing. So yeah, we'll put them on. Is that okay? Or I guess, yeah, okay. Yeah, that makes sense. That's a good idea. Yeah, so I basically said that the marks have been increased because they were giving them more credit for identification versus making observations, and I said that there were a couple of comments which were perhaps unnecessarily